All right, guys, welcome back. So let's try another example of Hardy-Weinberg, working with that same idea of those sickle cells and that sickle cell recessive disease. But instead, let's take a look at what this looks like in the African populations, where I now have a 4% homozygous frequency for sickle cell. So again, remember, sickle cell disease is recessive. So that means that its genotype is homozygous recessive, and so we start off with that Q squared. Now remember, when we do this, we look at that frequency of 4%, but let's try this again. Hardy-Weinberg prefers to use decimals. That's how this works. So we're going to turn that 4% into a decimal, and so I end up looking at 0.04 as that frequency. Now remember, when we do this, I need to get Q by itself. So if I take the square root, I should say, of Q squared, that gets me to Q, but this is my value for that. So I need to take the square root of 0.04 to figure out what Q is. And so Q ultimately ends up equating to 0.2. Okay, now that I have the fact that Q equals 0.2, I can now rearrange that equation, right? The P plus Q equals 1 to get P by itself by subtracting Q on both sides, all right, and leaving me with P equals 1 minus Q. If I plug in the value for Q, P equals 1 minus 0.2, then I end up with 0.8 for P. Okay, now I can figure out the frequencies for my genotypes. So if my homozygous dominant is my P squared, right, this is 2PQ, and this is Q squared. So we figured out that P was going to equal 0.8, Q equals 0.2. Okay, so let's plug in those values. So if P squared is 0.8, and I square it, I come up with 0.64 or 64%. My heterozygous frequency is the 2 times that 0.8 times that 0.2. And so I end up with a frequency of 0.32 or 32%. And my recessives, let's just double check ourselves. So 0.2 squared gets me back to the 4% that I started with. So here's an interesting thing. When we go to comparing the frequencies in those genotypes between the populations in the African American population as opposed to the individuals living in Africa, there is definitely a disparity in the frequency of that sickle cell trait. It's much, much lower in the United States population than it is in Africa. So these are just kind of two thought questions here. Let's take a look at them. So number 6 is, why do you think the recessive alleles remain in the population at all? Why do they exist here in the US or in Africa, period, if presumably that sickle cell disease is deadly? So here's the reason why this continues to stick around. When we look at the populations, especially in Africa, but even still looking at populations of people from African descent, then the cases in which those environments change keeps the recessive allele around. So think about it. There's kind of two pieces that play into this. First and foremost, you are going to end up in situations where we look at individuals who are heterozygous for it, right? The HBS, HBA. These individuals don't know that they are carriers unless there are genetic testing or some other reason for them to have come across the fact that they know that. So if I go and cross two individuals who are heterozygous together, they're going to have a 25% chance of creating a child who has that sickle cell. Let's get rid of that A. All right, go back and do your Punnett squares, right? There's one allele, there's the second. So just doing those typical Punnett squares, you always end up with 25% of the population when you have two carriers who have the potential to now show this trait. Second piece to this is that it also isn't getting weeded out in the population because remember, being heterozygous carries its own advantage. So we end up continually seeing a slightly higher heterozygous frequency in places where malaria exists, because that malaria is a real threat to those populations. And by being a carrier, although you're increasing your likelihood of passing on the recessive allele and having children who have that recessive trait, that risk of producing a sickle cell child is, from an evolutionary standpoint, outweighed by the own protection that you get by having the single sickle cell allele where you are not showing the sickle cell disease, but you also have protection against malaria. Does that make sense? So that's the idea of heterozygous advantage, is that in certain situations, being heterozygous and having the potential to pass on a harmful recessive trait is actually outweighed collectively from the protection that you get from having that heterozygous genotype. Okay, let's take a look at number 7 then. If there's this idea of heterozygous advantage, why do we see a lower frequency of the allele causing sickle cell disease in African Americans as opposed to what we see as a frequency in Africa? And the case here really is that the environments are different. We don't really have a problem with malaria here in the US, and so as a result, that heterozygous advantage really doesn't exist here. And so because presumably those generations have lived here long enough, we're seeing a slow reduction in those heterozygotes because it's actually more advantageous to not pass the trait on at all here in the US because we're not dealing with that threat of malaria. So hopefully that makes sense.